Hello everyone. Are you ready for the next lecture? I am sure you are ready. In this lecture, we're going to learn the general process in designing a laterally restrained beam. As we can see here, there are 9 steps in general for us to carry out, to ensure the safety and reliability of the designed beam. Step number 1 until step number 7 are the design steps that must be carried out for the ultimate limit state design. The ultimate limit state is the design for the safety of a structure and its users, by limiting the stress that materials experience. The ULS is to comply with engineering demands for strength and stability under design loads. ULS must be fulfilled as an established condition. Meanwhile, step number 8 are the checking required for the serviceability limit state (SLS). Alright class, here let's do one example. Here, I will assist you on how to design a laterally restrained beam with the guideline given in the design process. This example is taken from the textbook, Design of Structural Elements. Okay, now let's us read the question. The question requires us to check the suitability of 356 x 171 x 51 kilograms and 1 erb section. The grade of the steel beam is S275. The beam is being loaded by 8 kN per meter and 6 kN per meter of permanent and variable actions respectively. Here the question, assume that the beam is fully laterally restrained. Which means, the top flange of the beam is being restrained by a slab. The beam is sitting on 100 mm bearings at each end. Do you know what is bearing? This picture shows an example of the bearing support of the beam. And finally, in this example the self-weight of the beam is ignored. This is the textbook that I was talking about earlier. Alright, ready to go. I am sure you are ready. Now, let's start with the first procedure. Determination of design shear forces VD and bending moments MED at the critical points. First, what you need to do is to find the design action FVD. The design factor for permanent action is 1.35. While the design factor for the variable action is taken as 1.5. As you can see, the design action is calculated as shown in the figure. Hence, inserted the calculated design action of 158.4 kN into the shown formula to find the design bending moment MED. Or, we can also calculate by using another way. As you can see here, we also can use the formula of M equal to WL square over 8. We still can get the same answer as previous, which is 158.4 kNm. However, bear in mind that this formula is only applicable if a simply supported beam is being designed, and when only a uniformly distributed beam is being applied. Besides, there is another options. You can also use a traditional structural analysis way. That is, applying the 3 equilibrium equation forces. This approach is recommended, as it is flexible to be used for any applied loading conditions. Using this approach, firstly, you need to find the reaction forces at support A and support B. In this case, the reaction forces at A and at B is equal that are 79.2 kN respectively. Once the support reactions has been calculated, thus, you can draw the bending moment diagram and shear force diagram, as shown here. To find the critical bending moment diagram, you need to find the location at which the shear force is 0. Maximum bending moment is occurred at the point where the shear force is 0. As you can see here, the shear force is 0 at the midspan. By cut the beam section into 4 meter, using the 3 equilibrium equation. Hence the maximum moment is calculated to be 158.4 kNm. In the most common cases, maximum design of shear force VD occurs at supports, while the maximum design bending moment MED occurs at midspan or supports. How are you going to ensure that the given beam section is adequate? For this, you are required to refer Eurocode BS 1993-1-1 2015, Clause 6.2.5. However, in general, design shear force VD must be less than the design plastic shear resistance VPLRD. Design bending moment MED must be less than the design plastic moment resistance MPLRD. However, in the case where the beam section is not given, a trial section should be chosen. For you to choose the appropriate beam section, firstly, you need to calculate the plastic modulus about the major axis WPL. The formula is given as shown here. Let's go to one example of how to choose trial section. OK class, please refer to your example question. According to Eurocode clause 6.2.5, the design resistance for bending about one principal axis of a cross-section is determined as highlighted in the red box. Based on the previous example, we know that the design bending moment is 158.4 kNm. To calculate the plastic modulus, the design bending moment is inserted into the equation. Finally, you will get the plastic modulus of 576,000 cubic millimeter. From the figure, find the nearest value of the plastic modulus, that is above 576 cubic centimeter. Next, choose the trial section accordingly. Here, we can choose in the size, between the range of 356 x 127 x 39 kg/cubic meter to 356 x 171 x 67 kg/cubic meter. For your information, in real design, engineer must propose the trial section. However, in this lecture, the section is given to simplify the explanation process. This trial section approach will benefit you when you carry out the ECS571 design project.